video is designed to give you a working understanding of AC circuitry as you will install and troubleshoot it. We're going to follow our oversimplified AC circuitry from power generation to transmission, distribution, and finally utilization, taking extra care to define some tricky concepts around the so-called neutral wire. Let's start our oversimplified journey at alternating current, or AC generation. Let's first talk about some of the words we use to define electricity. I think it's easy for all of us to imagine pressure when it relates to water distribution systems. We all understand that there's always water pressure behind this valve, whether it's open or not. What's causing the pressure? A pump usually. That pump is always running and providing constant pressure, so when you open this valve, water is forced out at a predictable and constant rate. The pressure can be thought of as potential, as in because of the pressure behind the water in the pipe, there's the potential for water to flow if I open this valve. So we understand that pressure is the thing that makes the water flow. How much water is flowing? That's the volume, which can be changed through pipe size or restricting the valve opening size. The volume of flow can be thought of as current, as in the current of a stream. Now let's relate these concepts to electricity. Getting electrons to move in a circuit requires pressure, electrical pressure, in the form of voltage measured in volts. Voltage can also be referred to as potential. The volume of movement of electrons is called the current, measured in amps. This flow can be restricted by resistance in the conductor or the load devices. A conductor is generally considered anything that is a low resistance part of an electrical circuit. Most often we think of copper or aluminum wire, but a conductor can be a solid bus bar as well. Conductive materials, including your body, can become unintentional conductors if they become part of the electrical pathway or circuit. You have to have voltage or pressure to have electricity. You have to have a complete circuit to have a flow of electricity or current. Electrical pressure is generated by moving a magnet and a conductor relative to each other. That's relative movement. So if you move the conductor past the magnet, or more commonly move the magnet past the conductor, electrical pressure is generated. Now that we have pressure, making a complete circle or a circuit with a conductor will allow electrons to move. Which direction the magnetic field is moving relative to the circuit and the polarity of the magnetic field will determine the direction the electrons will move in the circuit. Changing the direction of the movement of the magnetic field relative to the conductor or changing the polarity of the magnetic field will change the direction of the electrons in the circuit. Now let us look at an imaginary AC generator. A magnet is placed at the end of a rotating shaft. The rotation of the shaft could be achieved by the movement of a turbine at a dam, a steam-powered turbine using heat from coal, or really anything. You just need rotation. The magnet has invisible lines of magnetic force on either pole. The magnet is situated at the middle of a circle with 3 coils connected in 3 individual circuits, 120 degrees apart from each other. As the shaft is turned, the magnet turns and moves relative to the coils. The direction of the magnet's movement never changes, but the polarity and the strength of the magnetic field relative to each coil is always changing. Due to this change, electrons in each coil will start moving in a direction, speed up, reach a peak speed, slow down, reverse direction, and do it all over again. The electrons are moving in these 3 circuits because the moving magnetic field is putting pressure on them. Pressure is expressed in volts. Whether or not the circuit is complete, the pressure will still be present. If the circuit is complete, the pressure or voltage will induce the electrons to move through the circuit. The actual movement of electrons is current, which is expressed in amps. Of course, in an alternating current circuit, the pressure is obviously not constant, neither is the current. That being said, in practical applied terms, it's as if it were constant. When we speak of voltage and current in the field, we speak of them as constants. If you graph this behavior for one of these circuits where the pressure and direction of pressure applied to the electrons is the vertical axis and the time elapsed is the horizontal axis, you will get the familiar looking sine wave. One cycle goes from 0 to peak voltage in one direction through 0 to peak voltage in the other direction and back to 0. The number of times the cycle is repeated in 1 second is the frequency, expressed in hertz. In North America, generally speaking, circuits have a frequency of 60 hertz, meaning the cycle is repeated 60 times a second. Though we think of the voltage being one specific number, like 120 volts, for example, in an AC circuit the number is always changing. The number we read on our multimeter is an expression of the amount of work an AC circuit could do if it was a DC circuit. I think that's as far into the weeds as we need to go on that. As long as you understand that each circuit in this generator will be changing polarity and strength throughout the cycle, you'll be fine. Let's again watch one coil circuit work. As the magnetic lines of force pass through the coil, a current is induced. The current strengthens, then weakens. Now the opposite pole of the magnet is interacting with the coil. The current is moving in the opposite direction. The current strengthens, then weakens. And this repeats over and over again. The other two coils are going through the same process, but 120 and 240 degrees out from the first coil. So while they have the exact same pattern, the same thing won't be happening at the exact same time. You can look up a three-phase sine wave if you like. It's the usual way to express the relationship of the strength and direction of each coil compared to the others over time. I'm going to use a different way to show this relationship. Let's freeze time on our imaginary generator. We have three circuits in this generator. Going clockwise from top, they are A, B, and C. A phase, B phase, and C phase, represented by the colors brown, orange, and yellow. At this point in time, the A phase coil is in between the two poles of the magnet. Therefore, no pressure is being applied to this circuit in either direction. You can see that the other two circuits or phases are being affected by the magnetic lines of force from the magnet, but in opposite directions because they are being affected by opposite poles of the magnet. Now let's unfreeze time and watch the relationship between the phases. Now let's put this generator to work. After generating the power at the plant, the first step to put it to use will be to step up the pressure or voltage to send power the long distances from the plant to the places where it is used. To increase or decrease the pressure or voltage in a circuit, a transformer is used. Transformers can have a few different configurations. In this instance, we have wired the connections from generator to the line or primary side of the transformer in a Y configuration. There are math reasons for why engineers use a Y connection on a generator, but I don't think it's important to understand those reasons. Just know that it's not unusual to use this connection on generators. Y connections can also be used on the load side of transformers because it gives the end user more voltage options. Don't be intimidated and let's crack straight into a Y connection. You're hopefully now comfortable with the idea that the generator has three coils. In our drawing, we'll use a squiggle to represent every coil, and a Y connection. One side of each coil is wired together at a common point. This wire is referred to as a neutral. I would like you to think of this central connection as a common first and foremost, as in this point is common to one side of all three generator coils. Now let's add a set of three transformers. For now, we're just showing the line side coils of each transformer. We'll get to it soon, but please accept for now that the line side of a transformer is just a coil of wires like the ones in the generator. As this transformer package is designed for three-phase power from our three-phase generator, there are three coils. This transformer package is also designed to be used with a line side Y connection, so one side of each coil is wired to a common. That common will be labeled H0 and will be connected to the common on the generator coils. Now the other ends of the line side coils are connected from the generator to the transformer package. A phase to H1, B phase to H2, and C phase to H3. What is line and what is load can often differ from which piece of equipment you're looking from. In this instance, the generator is line side and the transformer is load side. The connections we made are on the line side or primary of the transformer and the load side of the generator. Let's talk a little bit more about the common or neutral wire here. In a situation where there was no load or a completely balanced load between all three transformers and thus all three generator coils, there would actually be no current flowing on the common wire H0. This is why this wire is called a neutral. It's a bit hard to wrap our heads around, at least for me, but you could have 20 amps on each one of these phases, and that would mean the current you read on the neutral would be 0. Here's the formula for finding the current on the common or neutral in a 3-phase Y circuit. I'll put it in the video description. It's math and it works. Don't feel obligated to understand this math. Project engineers will figure this stuff out. Just be aware of how this works in general terms. In the real world, though, there's never a completely balanced load between all 3 circuits, so the common or neutral carries the imbalance. I promise you that if you were to put your body between the line common and load common of a Y circuit, you will find that it is decidedly not neutral. Furthermore, disconnecting the common or neutral in this configuration would cause the voltage to divide in unpredictable and undesirable ways across the coils. Whether or not the math says there's 0 current, this so-called neutral is an important part of this circuit and should not be disconnected under load. This is the reason why sharing neutral wire between multiple branch circuits, like multiple lighting circuits for example, is not recommended. The code has specific requirements for this situation, but try and avoid it. Before we move on, let's talk about the pressure relationship here. A 3-phase circuit's voltage will be listed by its line-to-line or phase-to-phase voltage. That means if this is a 480 volt generator and I put my 2 multimeter leads on any 2 phase wires, I will read 480 volts. If I put my 2 leads across a phase conductor and the common or neutral, I will read 277 volts. In a Y connection, which means it has a neutral, the line-to-line voltage will be 1.73 times the line-to-neutral voltage. That's because the phases are 120 degrees apart. Once again, don't worry about the math. You'll get familiar with common voltages and understand what's Y or delta derived. Let's have a closer look at how a transformer works. Each transformer is actually 2 coils, a line-side coil and a load-side coil. The current passing through the line-side coil creates a magnetic field that is expanding, collapsing, changing polarity, expanding, and collapsing again. At the same time as the pressure from the generator is strengthening, decreasing, changing direction, strengthening, and decreasing. The changing magnetic field on the line side of the transformer will create pressure on the load side of the transformer that mirrors the line side through a process called inductance. Again, this is as far down the rabbit hole as we probably need to go, unless you plan on making DIY transformers. One thing I'd like to note about my crappy animation is the output voltage is determined by the ratio of coils from the line side to load side. Since my animation shows a 1-to-1 ratio, the voltage would actually be the same on both sides. This isn't what I said we were trying to do. I told you that we were trying to step up the voltage for transmission. It's a small detail, and you won't be counting coils in the field, but sorry about that anyways. This is happening across all 3 transformers with the same phase relationship as before. Now let's look at the connections on the load side of the transformer package. Each coil on the load side of the transformer is 1 phase. We're going to connect the load side of the transformer in a delta configuration, which I believe is the most common configuration for long distance power transmission, but I could be wrong there. It might be easiest to imagine how these coils connect in a schematic drawing first. Each coil has each of its sides connected to another coil, creating a triangle-like arrangement. Each terminal is common to 2 coils. They are labeled X1, X2, and X3. If you put your meter on any 2 points, you are reading phase-to-phase voltage or line-to-line voltage, which is the rated voltage. That means if you are metering a 3-phase 480 volt circuit, you will put your meter leads on 2 wires at a time, and you would expect to see 480 volts displayed on your meter each time. There is no neutral here to put your meter on. Let's go back to the original drawing, and you can see that the individual transformers in the package need not be arranged in an actual triangle for the wiring to be in a triangle or delta configured. Delta configuration has no neutral. Let's finish off our imaginary circuit by putting a load at the end, a motor. We're not going to dwell on a 3-phase load right now. I don't think it helps the progression, but I made the animation, so let's just suffer together. Alright, we have shown how power is generated and how it is stepped up for transmission. But what happens next? Power is transmitted at super high voltage on transmission lines to a point somewhat physically close to where the power consumers like houses, stores, or factories are. Taps will be connected from the transmission lines to a step-down transformer package called a substation. The step-down transformer is probably a delta-to-delta connection, meaning that the line side of the step-down transformer package coming from the load side of the step-up transformer package is a delta connection, and the load side of the step-down transformer package will be connected in delta as well. It's not uncommon for the local supply wires or the load side of the step-down transformer to be 480 volts, so we'll stick with that for now. Though other voltages like 4160 are somewhat common as well. These can be configured in all kinds of ways. We're just using 480 because we have to pick something to use. Keep in mind that the behavior of the electricity at this transformer package will be the same as at the first one, and this will be true throughout all the electrical infrastructure all the way down to your house circuits. Little electrons jiggling back and forth, the pressure strengthening, peaking, lessening, changing direction, and repeating, all at 60 hertz or whatever the system's rated for. So now we have three-phase 480 volt power jiggling right through your neighborhood on wires you might recognize. If power is getting dropped for residents, two-phase wires from the local distribution net are tapped to connect to the line or primary side of a single-phase step-down transformer. Notice I'm not saying transformer package this time. This time it's an individual transformer with two wires connected to the line side. The load side of this transformer has two connections going to the house panel. If you were to put your meter on these two connections, you would read 240 volts of pressure. These connections you might be familiar with. They connect to the two copper bus bars in your panel that the breakers are connected to. So what's the third wire? The mysterious neutral. It's not a neutral. I'm not fond of that term. It is a current carrying conductor that is connected to the physical center of the load side coil. If you connect one lead of your meter to the center tap and the other lead to either bus bar, your meter will display 120 volts. This is because we've created another circuit path that only experiences half of the pressure exerted from the line side of the transformer. Let's redraw this to better understand. Forget the panel for a minute, right off the transformer. Let's pretend that we have a 240 volt rated light fixture to wire. We wire it like this, line to line, but really it's a complete circuit. The load side of the transformer is experiencing pressure to jiggle the electrons back and forth at a pressure rate of 240 volts. If the circuit is complete, the light will shine. Let's now pretend we have a 120 volt rated light fixture to wire. The load side of the transformer is experiencing the same pressure, but now we are exposing the circuit and the fixture to half of the pressure, thus 120 volts. We could use the other half of the transformer with the same results. One thing to remember is that if you touch the bare copper in a wire with white insulation, you are most probably touching a direct path to center tap of the transformer. I would under no circumstances start to think of this wire as neutral or not dangerous. When communicating with other people, of course you're going to call it the neutral wire, and that's acceptable. But do not sleep on this wire. The code refers to this wire as the grounded conductor for reasons we will shortly get into, but just remember for your own good, it is a live circuit conductor. If you touch this wire and simultaneously touch another wire or bus bar that is connected to another part of that transformer or any other transformer, then you are completing a circuit with your body and you will get lit up. We've now left the power company's world and are entering the area of the inside wireman. Let's take some care to go over residential service and its branch circuits. Let's just look at the load side of the transformer on the street. Unfortunately, I labeled it line side. Sorry, once again. Line to line, it's 240 volts. And line to common, or neutral, it's 120 volts, as is the other line to neutral. Now let's add a meter base so the power company can get paid. Just imagine the rectangle is the metal enclosure and the circles are the wire terminations, please. Let's add a manual disconnect switch so that all power can be disconnected from the residence if need be. Let's add a main breaker panel. In this type of panel, the feeder wires are connected to a breaker in the panel. The load side of the breaker feeds the bus bars pictured here in orange. You're going to have to use your imagination a bit, I know. The neutral bus is on the left, and we'll talk about the ground bus in just a bit. In any case, the breakers will snap onto the bus bar. The bus bar is built so that the breakers alternate vertically which bus bar they are connected to. If the main breaker is closed, then these bus bars will be energized. Be very careful around exposed electrical parts, and always cover your butt. Lock out and tag out. Many times the breakers or the fuses are located before the panel, maybe adjacent to the meter in place of the manual disconnect. In that case, this would be a main lug panel with no main breaker, and the feeders would attach pretty much directly to the bus bars. You might have to go find the disconnect to de-energize this panel. We're going to stick with the main breaker example for now. Let's start wiring this thing up, starting with transformer to meter base. Please don't get hung up on the colors I picked to represent the wires. These aren't real-world color codes, just for ease of visualization. These wires are considered service conductors and are usually the responsibility of the power utility company. Wires from the meter base to the disconnect. In this drawing, this is just a manual disconnect. Now the feeders to the panel and the neutral are common. This wire isn't switched by either the disconnect or your breaker, so we're going to show it just passing right through the panel. The power company installs their meter and completes that connection. Let's close the disconnect and complete that connection. And now the panel main breaker is closed, and we have potential all the way to the bus bars. If we meter the bus bars, we can see 240 volts of potential or pressure. There's also a path to the center of the transformer, so line to common we have 120 volts. Same here. It's time to discuss overcurrent protection. Any conductor has a limit to how much current it can carry. The bigger the conductor, the more it can carry. If the limits of the conductor are exceeded for long enough or far enough, the conductor will actually melt. This is obviously bad for many reasons, and it's a serious fire risk. A conductor can be overloaded by simply adding too many loads, like too many lights and appliances, or devices can malfunction or wear out, causing abnormally high loads. A conductor can also experience a short circuit. That is, if there is a direct path through the circuit without significant resistance. A transformer coil or any electrical source can't just be wired in a circle. There must be some kind of resistance in the form of loads like lights and appliances, transformers, etc., or the circuit should be open like it's pictured here. If the circuit is completed without resistance or shorted like pictured here, massive amounts of current will flow through the circuit, eventually melting something somewhere. This is the circuit that is being completed in this example. Every part of that circuit is being exposed to excessive heat, and any part of it can fail, including the wire terminals, breakers, meter connections, or the transformer coil. All of those things I just mentioned should have been designed to carry the expected current. If current exceeds design, the circuit breaker should trip almost instantaneously and open the circuit. The main breaker in this panel is a two-pole breaker, meaning that two separate contacts close together and open automatically together. Let's clear the short and close the breaker. Here is a short from line to common, or line to neutral. Here's the current path. And both poles of the breaker are disconnected. Let's clear the short and close the breaker. A short from the other line to breaker would of course have similar results. A branch circuit is a circuit from the final overcurrent protection device. This is where you're going to find your loads like lights and stuff. We install a circuit breaker on the line bus, then close the breaker. From the wire terminal on the closed circuit breaker to the transformer common, we read 120 volts of pressure. We imagine a load device, doesn't matter what, this one is a 5 amp device, and wire it from the breaker terminal. This wire is often identified as the line, and wire the other side to the neutral bus or transformer common bus. Since the breaker is closed and there's no switch in line to interrupt it, current will flow like this all the way through the circuit. We can move the breaker down one space so that it connects to the other line bus, and you can see how the current will flow. If there's a short circuit on the branch circuit, the smaller branch circuit breaker should trip instead of the main breaker so that the other branch circuits are unaffected. Loads on AC circuits can be installed in parallel, like this, but not in series like this. Loads in series will change the circuit voltage. You've probably seen two-pole breakers. Let's install one on this panel. A two-pole breaker is a line-to-line circuit, so 240 volts in this instance. Here's a 240 volt load. 240 volt loads in a residence are usually larger appliances like an oven or a clothes dryer. It gets wired line to line. And this is the circuit path. Notice that it travels through the entire transformer coil. Most residential appliances will have a neutral as well. This is because the control circuits and displays only require 120 volts. Internally, these parts are wired from line to neutral. Time to take a look at the ground bus, which is connected to and made common with the neutral bus. Green-clad conductors from the ground bus are connected to all metallic parts of a system that could become energized, like the breaker panel, the disconnect box, and the meter base enclosure in this picture. These conductors are called grounding conductors, or the equipment ground. They go everywhere circuit wires go. The conduit, switches, fixtures, receptacles, and metal boxes will all get connected to an equipment ground. If any part of an energized circuit is connected to metal that is connected to the ground bus, electricity will flow through the grounding conductor to the ground bus, then through the neutral bus, and back through the transformer. The unlimited current that a short circuit allows will cause a circuit breaker to trip, opening the circuit. The grounding conductor gets its name because it is also connected to earth, like the actual dirt. This connection is to dissipate the enormous energy from a lightning strike. Under almost any condition other than a lightning strike, including short circuit, the earth connection has no function and carries no current. Because the neutral conductor in this system is connected to the grounding conductors, it is also named the grounded conductor. Grounding is green, grounded is white. You're going to hear this a lot in school or wherever you study the code. Let's do one more example of a full circuit, this time with a switch and a grounding conductor. The grounding conductor is attached to the metal box that the switch is in, as well as to the box for the light. The switch is open, so the light is off. Let's close the switch, and now the light is on, drawing current through this pathway. If the circuit becomes shorted to the switch box or the light box, then the current takes the path of least resistance through the grounding conductor, back through the transformer, and the branch circuit breaker opens. I think that's plenty for one video. Hopefully you've come away with some useful information. I certainly have a newfound respect for animation, audio, and video editing in general. If you notice any errors, please point them out in the comments, or feel free to add any useful information or sources as well. Bye for now.